Here we are in a quantum mechanics class, and suddenly they bang you with J hat for the operator plus, and they say that's a raising operator. And now if it works on a cat, which is called J, M, then all kinds of horrible things happen. There's some square roots. Who ordered this? Who thought of this trick? Is it a trick? Doesn't make any sense whatsoever. It's the simplest possible thing if you think of it in terms of matrices. So everybody wants to know what's the deal with this raising and lowering operators? What kind of trick is it? Who invented it? It's totally elementary. Just forget about browsing cat, think of matrices. What's the simplest basis for 2 by 2 matrices? 2 by 2 matrices have 4 entries, so here is a possible basis. I'm cheating just a bit because I'm pretending matrices are real, but Hermitian matrices are essentially real, so it's okay. Now, there's a problem with the first two guys. They are not traceless. The other two guys, a little weird, but you know them. This guy is a raising operator. Every time you apply it, the things go one diagonal up. Now, you don't see diagonals yet, but if you do it for 3 by 3 matrices, you'll see them. And eventually, you end up with an empty matrix with matrix of zeros. The other guy is a lowering operator. Every time I apply it, everybody goes one setting down until you run out of everything and you get a zero. These guys we don't like because by themselves they're not Hermitian, and these guys we don't like, but we can combine them in such a way that we get identity matrix, which we don't have to care about because identity is identity, it's always there. And then there's a traceless matrix. And the trick with these guys is to combine them in such a way that when you add them up, you got a matrix whose transpose is itself, so that's a Hermitian, and you're allowed to multiply them by any number. So when you take a difference and multiply them by I, that's also Hermitian. So that is a good basis. And you might recognize this as Pauli matrices. The three of these guys. There's one observation about it. This is, always there, identity, and its trace has a special role. If I take a trace of a matrix, in other words, add up everybody on diagonal of the identity, you get 2, and that's dimension of the space. Now notice, it's linear algebra, so these bases are fine. This space is a little bit better because they're cooked up to be self-adjoint or Hermitian. But raising and lowering is kind of trivial when you think of it this way. A little bit hard to see anything very impressive about this. When you square this matrix, you get 0, no big deal. It's more obvious and more instructive when you do it for 3 by 3 or higher matrices. So if you call this a raising operator, in other words, a matrix. Then when you apply this guy twice, you end up with a non-zero matrix. So you have to apply it 3 times, but you end up with a 0. Obviously, if you go below the diagonal and apply it, you get minus. You can see that you can add this thing up from Hermitian guys. So, how do you get Hermitian guys? They look like something on diagonal. Those are real numbers. And then there is something here. And by Hermitian adjoint property, you don't have to specify the guy down here because they're given by complex conjugate transpose or Hermitian matrix. So you just need a diagonal and guys off diagonal. Their number is this. So that is a way to get Hermitian bases. Then there's some matrices you can combine. There's obviously identity, but then there are matrices which are on diagonal, so they commute. with each other because they're diagonal matrices, but they have different eigenvalues because they're different diagonal matrices. So these guys are called center. So as we go to more symmetries, there might be more commuting quantities. Remember, whenever you have commuting operators, that's a big deal. That's our J pluses and J squares and stuff like that. And then you can also combine these things into things that are off diagonal. They're not Hermitian because you complex conjugate and get something else. So they're not Hermitian operators. But if you apply them several times, they march off and you apply them to any vector. That vector just marches off over the edge until sufficient number of applications gives you zero. In this case, there are 3 of them. And those are the raising and lowering operators. But if you write them in terms of operators, brass, cats, etc., they look very mysterious. And if you look at them as vectors rather than looking at these operators, the states have to be normalized. So you get crazy square roots of j plus 1 minus m minus 1. And it's good. We have to keep care of all that stuff. But it isn't some weird trick. It's the simplest thing you could do. And from it comes so-called Cartan killing classification of all compact symmetries, continuous symmetry, which are all possible generalizations, of rotations on spheres in higher dimensions. That's called theory of Lie groups. And you use combinations of commuting operators and raising and lowering operators around various eigendirections of these guys. And that gives us all of the particle physics, basically, magic numbers of particles, so-called eightfold way, SU3 and stuff like that. So it's not so mysterious. It's just the simplest possible thing you could think of.